Hello everyone, today I'm glad to introduce our fuzzing work, group-based Corpus scheduling for parallel fuzzing. Facing complex program, the efficiency of fuzzing is challenging. Recently, researchers deploy parallel fuzzing to speed up testing. In the general framework, parallel fuzzing consists of master node and subnodes. The master node maintains the global information, such as global coverage information, global interesting states. And the subnodes are usually responsible for the specific fuzzing. We found that the existing work has the following three limitations. First, they focus on the task division in one-stage mode. So what is one stage? We consider each instance to fuzz continuously until the end of the whole test. We call this one-stage mode. In this mode, all instances collaborate by exchanging states, but with the large amount of historical information generated during the fuzzing, this information will interfere with the states. For example, Corpus applies some scheduling strategies, but the states cannot actually affect the sub-instance. The second limitation is that their local corpus are the same or similar. For example, airfill, libfuzzer, and unifuzz. They don't consider enough the difference degree of each local corpus. Since the fuzz engine adopts same mutation operations, the test case will through the same path, finally resulting in the task conflicts. The last important issue is that the research are more focused on the task division. They ignore the important corpus scheduling, as well known, an importance of a high-quality initial corpus for fuzzing. And the says from master node to sub-instance is a typical corpus construction process. In order to cope with the existing problems, we investigate the multi-stage parallel mode. The whole testing process is divided into multiple stages. Each substage is a new beginning. At the beginning of each substage, the master node always constructs the initial local corpus for them. At the end, the test results are merged. And then we aim to solve the two challenges by constructing the high-quality corpus. Based on the previous analysis, we proposed a group-based corpus scheduling strategy, which is mainly divided into three parts. The first one, dividing the global corpus into different sub-stages. The second one is to calculate the energy and different scores of groups by using coverage features and size features. The third part is to combine the two scores to select the target groups and finally generate the local initial corpus. The first part. Now, some real-world programs have more than 10,000 interesting states, and maintaining coverage information for each state is expensive. So we divided the global corpus into different groups and maintaining feedback information for each group. This method can save additional overhead. Second, in general, size of a seed often directly affects the throughput. So we group the global corpus based on size features. And last, please note that the number of local corpus and the length of substages both are important factors affecting the multi-stage mode. In this work, we use an empirical value, and we will further consider the related contents in our future work. The second part is the score calculation for each group. For energy score, our goal is to increase the code coverage as much as possible. So we choose the number of covered basic blocks and the average speed as the feedback. The weight of the word is adjusted by alpha. For the difference score, which mainly assesses the difference degree between two local corpus, it is calculated by considering the value and the number of basic blocks between two corpus. Different basic blocks contain different values is a common thing. So, inspired by entropy work, which argues that the more valuable seeds are rich in information entropy. So, in our calculations, seeds that hit low frequency basic blocks contain more entropy values. So they tend to reveal richer program behavior. The last part is to select the target groups for all parallel instances. Since two scores depend on different state features, using one score singly will have a conflict impact on the other. So we choose the top groups with higher overall ranking. And finally, randomly select the seed from each group to build the corresponding local corpus. In the evaluation section, we choose 18 reward programs to compare bug detection, branch coverage, test throughput, whether additional overhead is entrusted, and how scalable it is. Additionally, we also deployed some experiments in Google Fuzzing service. In terms of bugs detection, glibfuzzer crashes the target group program faster, more often, is more stable over 10 travels of experiment, and additionally found more reward bugs. In terms of branch coverage, glibfuzzer also received a significant boost. For throughput, glibfuzzer generates 19 times more test case on average than the libfuzzer. Most important, in the final global corpus, the average seed size of glibfuzzer is about half that of libfuzzer. In terms of additional overhead introduced, Corpus destination is a relative high overhead operation, except for programs contain too many seeds and slow execution. Other programs overhead is negligible. libfuzzer contains two parallel modes, P is the one-stage mode, and F is the multi-stage mode. G is R2, glibfather. It is obvious that the multi-stage parallel mode performs better as cores and the time bucket increase. We found that the additional Corpus scheduling process introduced can complement and collaborate with the internal Greybox set scheduling process. So we believe that parallel fuzzing can not only reduce the testing time, but also improve the bottleneck of code coverage. Second, we prevent the concept of multi-stage parallel gray box fuzzing, and we found the local Corpus construction is a key step affecting the performance of it. And last, this work was also merged into the main branch of libfather, and most important, we relied on our glibfather to detect a large number of real-world bugs and reported them to the vendor. In closing, thanks for listening again.